Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome to today's lecture on systems with purge. What is purge? Purge is basically a process where some of the components are removed to ensure that there is no accumulation of unwanted material or inerts which would reduce the efficiency of a process. So this prevents buildup of these materials which can usually happen during recycle. So if you look at this process, you have a separator which takes out some of the material that can be recycled back into the system, and whatever is being recycled, if it continuously is recycled without actually having a purge, you might end up with a higher concentration of the inerts or undesired materials. So this would drive down the efficiency of the process of interest. To ensure this does not happen, you have a stream called the purge stream, and this purge stream makes sure that the concentration of the unwanted components and the inerts are kept at a desirable level to ensure process is effective. Here are some example problems which will help us understand this concept in a better way. So the gases are generated by burning coal, which is carbon monoxide and hydrogen, are used to produce methanol, and the reaction is given. The figure which is shown here shows the process, and a purge stream here is used to maintain that the exit concentration of methane is only 3.2% and does not exceed that. This also prevents hydrogen buildup. The once through conversion of carbon monoxide in the reactor is 18%, and you are asked to calculate the moles of recycle, methanol and purge per mole of feed which is sent into the system. Also you are asked to calculate the purge gas composition. So you have the feed which is given, with the composition of the feed is also given. You have a reactor and a separator. Whatever is coming out of the separator is either the methanol product, or you have a recycle stream which is then split into two components, one being the recycle and the other being purge, and the recycle is sent back to be mixed with the fresh feed. So this is what the process is. Now let us see how we can go about solving this problem. Just like any material balance problem, we will start with the basis. So the basis for this system would be 1 mole of fresh feed. It has been given in the problem that we have to calculate all the values per mole of fresh feed, so we use that as the basis. So we can start with the overall system. So if we were to assume the overall system, we can write balances for the different components. So let us first write the balance for methane, because methane is a non-reacting component, it would be a simple balance to write. So we will have the methane balance as input equals output at steady state. So giving us an input of 0.002 times F, and your output would be Z times P, where Z is the mole fraction of methane in the recycle stream. So as there is a splitter which splits the recycle and purge stream, we know that the concentration of methane in both the recycle stream and the purge stream would be the same. So therefore the mole fraction Z can be used for the purge stream also. So that is why I am writing it as Z times P. Another information we have from the problem is, we do not want the concentration of methane to go beyond 3.2%. So this means the Z would be maintained at 3.2%, which is equal to 0.032. So substituting these values, we can get the value of P as 0.0625 moles. So this is the purge stream which is being purged from the system. So now to calculate the composition of the recycle stream and the mass of the recycle stream, we can write balances for the elements. So we can write the carbon, hydrogen and oxygen balances. So when we write the carbon balance, we would have input equals output at steady state. So the input for carbon for the overall system comes from the fresh feed. So this would be 0.325 times F. So 1 atom of carbon enters in the form of carbon monoxide. So, that would be the fraction of carbon in the carbon monoxide plus 0.002 times F, giving us the amount of carbon which is entering in the form of methane, and we have carbon leaving in the form of methanol. So, which would be E plus carbon leaving in the form of methane and carbon monoxide through the purge. So, that would be Y times P plus Z times P, which is 0.032 times P. So, now that we have this equation, we can simplify this, and we already know the value for P. So, using the values for F, P, we can actually write this equation as, substituting the value for F and P, we can simplify this equation to 0.325 equals E plus 0.0625. So, let this be equation 1. We can also write the hydrogen balance for the overall system. The hydrogen balance would be 0.673 times 2 times F, which is the number of atoms of hydrogen entering in the form of molecular hydrogen, plus 0.002 times 4 times F, which is the number of atoms of hydrogen entering the system in the form of methane, and you would have the output as 4 times E, which is 4 atoms of hydrogen leaving with every molecule of methanol, plus X times 2 times P plus Z times 4 times P, which would be the number of atoms of hydrogen leaving per molecule of hydrogen and methane through the purge stream. So, now this equation can be simplified by substituting values for F and P, and we would end up with an equation that would be 1.346 equals 4E plus 0.125 x. So, let this be equation 2. We could also write a balance equation for oxygen. So, the atomic balance for oxygen would be 0.325 times F would be equal to E plus Y times P. This equation becomes 0.325 equals E plus 0.0625 times Y. So, what you see here is this equation is the same as the first equation you got, hence these two equations are dependent. Now, you still have two equations and 3 unknowns, the unknowns being E, X and Y. So, we need one more equation. What equation can we use? As X, Y and Z are the mole fractions, we know that X plus Y plus Z would be equal to 1. Now, using this equation, we have 3 equations and 3 unknowns. We can substitute the value for Z, which is 0.032, and we will get X plus Y would be equal to 0.968. Now, solving 1, 2 and 3 simultaneously, we can get the values for E, X and Y. So, we get E, which would be equal to 31.25 moles, and X is equal to 0.768 moles per mole, and Y is equal to 0.200 moles per mole. Now that we have the information about the methanol which is produced and the mole fractions of the recycle stream and the purge stream, we still are to calculate the amount of components which is being recycled, which is R. For doing this, we can choose different systems. So, looking back at the problem, the one information which we have in addition to whatever we have used is 18% single pass conversion. So, to use this 18% single pass conversion, we have to choose a system in a way that the feed enters and leaves the reactor only once. As we do not know the composition of the stream which is leaving the reactor, however, we know the composition of the stream which leaves the separator, we can choose a system which would be the reactor plus the separator, ensuring that we can use the single pass conversion and also perform all the material balances that are required. So, the system of interest for this part of the problem would be recycle plus separator, reactor plus separator. So, taking the reactor plus separator as the system, for the reactor and separator system we can write a carbon monoxide balance. Why do we choose carbon monoxide? Because that is the component for which we have the single pass conversion. So, this equation would be input minus output plus generation minus consumption equals accumulation. At steady state you do not have an accumulation, there is no generation because carbon monoxide is a reactant. So, you have input minus output minus consumption equals 0. So, the input term would be 0.325 times F plus 0.2 times R. This accounts for the carbon monoxide entering through the fresh feed and the carbon monoxide which is entering through the recycle stream, minus output would be carbon monoxide leaving through the stream which is then being split as recycle and purge. So, the flow rate for this stream which is leaving the separator would be R plus P times Y which is 0.2, and you have consumption term which would be 0.18 times input which is 0.325 F plus 0.2 R. Now, we have the values for F and P already. So, substituting them we can get the value for R. So, this is equal to 0. So, the value for R would be 7.06 moles. So, with this we have calculated the recycle stream also. Let us move on to one more example problem to ensure we have full understanding of how to perform these calculations. Again, for this problem we will also draw a flow chart which will help us understand how to convert word problems into flow charts and then perform necessary calculations. Methanol is produced in a reaction of carbon dioxide and hydrogen, and the reaction is given. The fresh feed to the process contains hydrogen, carbon dioxide and 0.4% inerts. The reactor effluent passes to a condenser that removes essentially all of the methanol and water which is formed and none of the reactants or inerts. The later substances are recycled to the reactor. To avoid buildup of the inerts, there is a purge stream which is withdrawn from the recycle. The feed to the reactor contains 28% carbon dioxide, 70% hydrogen and 2% inerts. The single pass conversion of hydrogen is given as 60%. You are asked to calculate the molar flow rates and the molar composition of the fresh feed, the total feed to the reactor and the recycle stream and the purge stream for a methanol production rate of 155 kilomoles per hour. Now, let us try to draw this into a flow chart. Looking at the problem, you have a fresh feed which is entering. This feed contains hydrogen, carbon dioxide and inerts. The only information we have about this stream is the inerts component is 0.4%. So, this is mixed with a recycle stream which then becomes a total feed entering into the reactor. So, the total feed information has been given. So, total feed F prime, we have been told that it contains 70% hydrogen, 0.7 hydrogen, 0.28 carbon dioxide and 0.02 inerts. So, this composition of the total stream has been given, and you have a reactor output which then goes into a condenser, and this condenser separates the product which contains methanol and water. So, this would be the product stream, and the rest of it is actually collected and either recycled back or it is purged. So, we have a purge stream. So, this is the purge stream, we will call this X, and the purge stream would contain hydrogen, carbon dioxide and inerts, and so will the recycle stream, hydrogen, carbon dioxide and inerts. So, the product, the total product stream would contain the methanol which has been produced, the water which has been produced, hydrogen, carbon dioxide and inerts all leaving the reactor. So, this gives us the flow chart. In addition, the problem also states that 155 kilomoles per hour of methanol needs to be produced. So, we will use that as the basis. So, the basis for this problem would be 155 kilomoles per hour of ethanol in the product stream P. Let us first consider a system where we have enough information about the compositions. For this reason, we will choose the system which is the reactor plus condenser. So, for this system we have information about the total feed, we also know the amount of methanol which is being produced in the product. So, using this, let us try to calculate what would be the total feed. So, what we have is 155 kilomoles per hour of methanol being produced. Looking at the stoichiometry, so you have 1 mole of carbon dioxide reacting with 3 moles of hydrogen to produce 1 mole of methanol. So, if 155 kilomoles of methanol is produced per hour, the amount of hydrogen which is consumed would be, so 1 mole of methanol is produced by consumption of 3 moles of hydrogen. So, 155 kilomoles per hour of methanol is produced by consumption of 465 kilomoles per hour of hydrogen. For the given system, we also know that there is a 60% single pass conversion, which means 60% of consumption results in formation of 155 kilomoles per hour of methanol. So, that would imply the consumption which we have calculated here, 465 kilomoles per hour of hydrogen, would account for the 60% of hydrogen entering into the reactor. So, this implies hydrogen fed in the total feed would be 465 divided by 0.6, giving a value of 775 kilomoles per hour. So, now that we have the information about the amount of hydrogen, we can calculate the total feed as total feed F prime would be equal to 775 divided by 0.7, giving you a value of 1107.14 kilomoles per hour. So, we can also calculate the composition of the total feed, so which would contain carbon dioxide at 28%, giving you 1107.14 times 0.28, giving you a value of 310 kilomoles per hour, and hydrogen would be 775 kilomoles per hour, and you have inerts which would be coming in at 1107.14 times 0.02, which is 22.14 kilomoles per hour. Now that we have all the information about the composition of the total feed and also the single pass conversion of hydrogen into the reactor, we can calculate the total product which is leaving the reactor by choosing the reactor as the system of interest. Let us take the reactor as the system, and we can write the relevant balances to calculate the amount of methanol and amount of water, hydrogen, carbon dioxide and inerts which would be leaving the system. So, obviously water is only being produced. So, your output would be equal to generation. Using the stoichiometry, the generation of water would be equal to the generation of methanol. So, we know that 155 kilomoles per hour of methanol is being generated. So, this means the generation of water is also at 155 kilomoles per hour. So, this would be the water which is leaving the system. So, output for water would be 155 kilomoles per hour. So, we can calculate the other things also. So, hydrogen is consumed at 3 times the amount of methanol which is being produced. So, we know 465 kilomoles was being consumed from our earlier calculations. The equation which becomes input minus output plus generation minus consumption equals accumulation then becomes input minus output minus consumption equals 0, because there is generation and accumulation getting cancelled. So, your output is equal to input minus consumption, which is 775 minus 465. So, your output for hydrogen would be 310 kilomoles per hour. So, for carbon dioxide you have an input of 310. So, and you again would have only consumption and output terms. So, this your output would be input minus consumption. So, the output term would be 310 minus consumption, which would be equal to the same amount of methanol which is being generated, because 1 mole of methanol is generated from 1 mole of carbon dioxide. So, this would be 155. So, your output for carbon dioxide would be 155 kilomoles per hour. As inerts are not taking part in the reaction, whatever inert is entering into the system will be leaving. So, your output for inerts would be 22.14 kilomoles per hour. So, from this we have calculated all the information about the P prime or the total product stream. So, for the total product stream, this is the information we have. For the total product, we know that it contains methanol at 155 kilomoles per hour, water at 155 kilomoles per hour, and it also contains hydrogen at 310 kilomoles per hour and carbon dioxide at 155 kilomoles per hour and inerts at 22.14 kilomoles per hour. So, this product stream then enters into the condenser, all the methanol and water leaves through the final product stream, and the rest of the components, which is the hydrogen, carbon dioxide and inerts, is split into the recycle and the purge stream. Now, we need to know how much is actually being recycled and how much is being purged. So, what would be the system we can choose to calculate these? So, we could write a balance equation. So, this total product then enters into the condenser, where methanol and water is condensed to form the product stream, and the rest of it is then sent to being split as recycle and purge stream. So, now that we have the information about hydrogen, carbon dioxide and inerts which is present in the stream that is being split, we can calculate the composition of the recycle stream and purge stream using these values. So, this particular stream which is leaving the condenser contains hydrogen at 310 kilomoles per hour and carbon dioxide at 155 kilomoles per hour and inerts at 22.14 kilomoles per hour. Using these values, we can calculate the mole fractions as hydrogen mole fraction would be 310 divided by 310 plus 155 plus 22.14, giving you a mole fraction of 0.6364, and similarly for carbon dioxide the mole fraction would be 155 divided by 310 plus 155 plus 22.14, giving you a value of 0.3182, and inerts would be at 22.14 divided by 310 plus 155 plus 22.14, giving you a value of 0.0454. Now that we have the mole fraction of the stream which is leaving the separator, we also have the information about the mole fractions and the compositions of the recycle stream and the purge stream. Now we can choose appropriate systems to calculate the number of moles of recycle and purge. What system do we choose? For identifying the recycle stream, we need to choose a system where the recycle would cross the system boundary. So, that we can obtain by choosing the mixing point. So, let us choose the mixing point, for which we have information about the total feed stream and the composition of the recycle stream, and also we know the composition of inerts in the fresh feed. So, taking this system as the mixing point as the system, we can write the total mass balance. Total mole balance for this system would be F plus R equals F prime, and we already know that F prime is 1107.14, and we can also write the inert balances. The inert balances would be 0.004 times F plus 0.0454 times R, which is the mole fraction of inerts in the stream R, would be equal to 0.02 times F prime. So, substituting the value for F prime here, we now have two equations with two unknowns, and we can solve for F and R, giving us a value of F as 679.33 kilomoles per hour, and we have R as 427.81 kilomoles per hour. So, the fresh feed which is being supplied to the system and the recycle stream which is being sent to the system have both been calculated. We now have the information about the recycle stream and the fresh feed stream. However, we do not know the composition of the fresh feed stream. We do not know how much of the fresh feed is actually hydrogen and how much is carbon dioxide. For identifying that, we still have to write more material balances. So, here we can write a carbon dioxide balance. Let us assume X1 is the mole fraction of carbon dioxide in the fresh feed. So, this would mean the carbon dioxide balance would be X1 times F, which is the input, plus your carbon dioxide in your recycle stream, which is 0.3182 times R, would be equal to 0.28 times F prime. Now that we already know F, R and F prime, we can calculate X1, which is the mole fraction of carbon dioxide in the feed, as 0.256. So, with this we have the composition of the fresh feed also. We already know the percentage of inerts, now we know the mole fraction of carbon dioxide. So, this means mole fraction of hydrogen in the fresh feed would be equal to 1 minus 0.256 minus 0.004, giving us a value of 0.74. 0.74 would be the mole fraction of hydrogen in the fresh feed. So, with this we have all the information about the total product stream, the product stream, recycle stream and the fresh feed. We still have to calculate how much of the purge stream is being sent out. How do we go about doing that? For calculating the purge stream, we need to choose a system where the purge stream would cross the system boundary. So, the easiest system we can choose would be the splitter. So, for the splitter we can write only one total balance. So, for the splitter we can write only one mass balance or mole balance which is independent. So, here we can write a mole balance for the total moles which is entering and leaving the system. So, the total moles which is entering and leaving the system is through this stream, and the moles which are leaving are through R and X. So, the output is R plus X. So, the input here would be all the components of hydrogen, carbon dioxide and inerts which is entering into the condenser. So, which we already calculated as 310 plus 155 plus 22.14. So, giving us R plus X equals 487.14. We can calculate X as 59.25 kilomoles per hour. So, with this we also have calculated the number of moles of purge stream which is being sent out of the system. We already have calculated the composition. To summarize, this is the data we have. Based on the calculations we have performed, we can summarize the final answer as we have fresh feed which is coming in at 679.33 kilomoles per hour, and you have total feed which is coming in at 1107.14 kilomoles per hour, and you have recycle stream coming in at 427.89 kilomoles per hour, and we have the purge stream flowing at 59.25 kilomoles per hour. So, with this we can also calculate the compositions. Let us just call them as F, T, R and P. So, let us calculate the compositions for the different components. So, we have CO2, H2 hydrogen and inerts. So, we have the streams feed as fresh feed would contain 25.6%, 74% hydrogen and 0.4% inerts, and we have 28% carbon dioxide, 70% hydrogen and 2% inerts in the total feed. Recycle stream contains 31.82% carbon dioxide and 63.64% hydrogen and 4.54% inerts, and the composition will be the same for the purge stream at 31.82, 63.64 and 4.54. With this we come to the conclusion of this problem. I hope you have understood the fundamentals associated with performing these calculations for systems with purge. In the next lecture we will talk about a summary of how to actually solve all these material balances. So, this would be a revision lecture where we will go through some of the fundamentals associated and whatever we have learned till now. Until then, thank you and goodbye.